Hello everyone, I'm back again with another chapter to discuss with you all. Today we are going to discuss about the actual air cycles and their analysis. Till now, we have seen that the efficiency of fuel air cycle is slightly lower than the air standard cycles, and the reasons behind this has been discussed in the previous. Now, we'll see that though fuel air cycles are closer to the actual cycles, but still they are a lot different than the actual cycles because of different losses that generally occur in the actual cycles and are not considered during the analysis of the fuel air cycle. Now these reasons or these losses can be grouped in four types. One is progressive combustion rather than the instantaneous combustion. Second is heat transfer to and from the working medium. Third is substantial exhaust blowdown loss. And fourth is gas leakage, fluid friction, etc. in actual engines. Now these losses results in lower efficiencies than the fuel air efficiency or the air standard efficiencies. Now let's discuss about the first loss factor. The first loss factor is called the time loss factor. Now, for air standard cycles and fuel air cycles, it is assumed that the combustion process takes place instantaneously. But in actual cycle, it occurs over a definite period of time. Now, in SI engines, the combustion is assumed to take place at constant volume. But in actual case, some change in volume takes place while combustion is in progress. The crankshaft usually turns about 30 to 40 degrees between the initiation of the spark and end of the combustion. Now, a time loss occurs during this process, which is called the time loss factor. Now, what happens due to this time loss factor is that the peak pressure is not obtained at minimum volume. In other words, the peak pressure, which should have occurred at TDC, now occurs sometime after TDC due to the time loss factor. As a result of this, an additional amount of work would have to be done, and this loss of work reduces the efficiency of the engine. Moreover, the time taken for this combustion depends on the flame velocity. Now this flame velocity on various factors such as the type of fuel, the fuel air ratio, and also the shape and size of the combustion chamber. And it is seen that the distance from the point of ignition to the opposite side of the combustion space also plays a very important role in this flame velocity. Now the time loss factor can be easily described by this diagram of Otto cycle. Now the actual diagram that has been drawn, that is the fuel air cycle, Otto cycle. Okay, what happens is that the Otto cycle was about to start at this point, somewhere at this point. The ignition was supposed to start at this point, but as the ignition takes some time to occur, combustion takes some time to occur, it starts a bit before the TDC, and what happens is that some losses are found. This shaded region gives the time loss factor. Moreover, the combustion ends over here. Now starts from here and ends over here. Now in actual case, we were supposed to get pressure at constant volume, but in the progressive combustion process, some change in volume has taken place. This shaded region gives the work that has to be done in order to complete this cycle, and this extra amount of work done is lost, and it is about 6% of the total heat, and as a result, this black shaded region gives us the time loss. that occurred in an Otto cycle. Now let's discuss about the second loss factor, that is the heat loss factor. Now we can easily say that all the different parts of the engine, you can say the combustion chamber, the head of the combustion chamber, the piston, all of those things are not at all insulators. They can conduct heat to some extent. Now heat is seen to flow from the cylindrical gases to the cylinder walls, and that heat is also lost to the water jacket or the cooling fins. Moreover, some heat enters the piston head and flows through the piston rings into the cylinder walls, or it is carried away to the engine lubricating oil, which generally is situated underside the piston. Now this loss of heat has been shown by the red shaded lines over here, red shaded region over here, and it is around 12 to 15% of the total heat. And this loss of heat due to the heat conducting property of the materials decreases the actual efficiency of the engine. The third point comes the exhaust blowdown. Now, what is exhaust blowdown? The loss of work on the expansion stroke due to early opening of the exhaust valve, exhaust blowdown. Now, the exhaust valves are supposed to open at BDC, but if they open at the BDC, then the piston has to work against the high cylinder pressures during the early part of the exhaust stroke, and as a result they are in reality not opened at BDC but are opened sometimes before BDC. Now if the exhaust valve is opened too early, then a part of the expansion stroke is lost. So the best compromise is to open the exhaust valve at around 40 to 70 degree before BDC, thereby reducing the cylinder pressure to halfway before the exhaust stroke begins. Now this can be explained by this diagram. Now the fuel air cycle gives the exhaust stroke as this blue line given by the pen. The red line gives the early exhaust valve opening case, and the black line gives the optimum exhaust valve opening. Now it is opened in such a way that at the BDC the pressure of the cylinder is 7 bar, but it is opened in such a way that the pressure is not that high. It is almost half of this pressure, that is you may say 3.5 bar, so that the extra work against the cylinder pressure has not to be done, as a result increasing the efficiency. From the previous diagram we can see that the exhaust loss of around 2% takes place in this shaded region, which has been shown in larger scale in this diagram. Now the fourth loss that we get are losses due to rubbing friction. These losses are due to friction between the piston and the cylinder walls, friction in the various bearings, and also the energy spent in operating the auxiliary equipment such as cooling water pump, ignition system, fan, etc. Now the piston ring friction increases rapidly with increasing engine speed. It also increases with increasing mean effective pressure. The bearing friction and auxiliary friction also increases with engine speed. The efficiency of an engine is maximum at full load and decreases at part loads. It is because the percentage of direct heat loss, pumping loss and rubbing friction loss increases at part load. Now one of the most important topic of this chapter is the valve timing diagram. According to the air standard cycles, it is seen that the intake and exhaust valves are supposed to open and close at top dead centers and bottom dead centers. But in actual case, they are not opened or closed at the TDC or BDC. They are opened or closed either before TDC BDC or after TDC and BDC. Now, what is a valve timing diagram then? Now, the valve timing diagram is a representation of the positions of the crank when the various operations like inlet valve opening, closing, exhaust valve opening, closing, and closing, and also beginning and end of various strokes are shown. So, in a valve timing diagram, we will show the crank angle at which the various operations like opening and closing of the inlet and exhaust valves and the beginning and end of the compression and power stroke takes place. Now, I will discuss the intake, when the intake opens, when the intake closes, when the exhaust opens and when the exhaust closes using two diagrams. The two diagrams are discussed because one diagram is at low speed and one diagram is at high speed when the engine runs at high speed. Now, these are different due to certain different reasons that will be discussed along that. Now, this is the diagram or valve timing diagram at low speed. Now, this line in blue gives the BDC, that red line gives the inlet closes and inlet opens. These black lines give the exhaust closes and exhaust opens. Now, the different strokes have been divided into different colors. The red color circular line gives the intake. The blue color over here up to this TDC gives the compression stroke, and this later part gives the power stroke, and the black color line gives the exhaust. Now, at low speed, it is seen that the inlet opens around 10 degree before the TDC and it closes at around 10 degree after BDC, and after that the compression stroke takes place up to TDC and then the power stroke is done. But the exhaust opens at around 25 degree before BDC and the exhaust remains open till 5 degree after TDC. In the similar manner, if we look at the valve timing diagram at high speed, when the engine runs at high speed, we'll see that the intake opens at 10 degree before TDC. The intake stroke takes place up to 60 degree after BDC. After that, the compression stroke takes place up to TDC and then the power stroke up to this part. Here, the exhaust opens 55 degree before BDC and finally the exhaust closes at 20 degree after TDC. Now, there might be a question that why do we open and close the exhaust and intake valves a bit before or after the TDC and BDC. Now, if we consider the example of the intake, when intake opens, it is seen that both at high and low speed it opens at around 10 degree before TDC. Now, why does it happen? Why does we do that? Why do we need to do that? The sole reason behind this purpose is that to ensure that the valve will be fully open and the fresh charge starts to flow into the cylinder as soon as the piston reaches TDC. So before TDC, the valves take some time to open completely, and so the valves are generally are a bit before, at you may say at 10 degree before TDC just to ensure the complete opening of the valve so that the fresh charge can easily enter inside the cylinder when the piston reaches the TDC. Now, in case of low speed, it is seen that the inlet closes at 10 degree after BDC, and at high speed engine, it is seen that the intake closes at 60 degree after BDC. Why does it take place? Now see, during intake, when the piston moves towards BDC, the fresh charge gets drawn into the cylinder at high velocity. Now after reaching BDC, when the piston starts moving towards TDC, the inertia of the incoming fresh charge tends to cause it to continue to move towards the cylinder. A low engine speed, in low engine speed, what happens is that the charge moves inside the cylinder with slow speed in comparison to engine at high speed, and its inertia is also relatively low. Now, if the intake valve remains open much beyond the TDC for low speed engine, the upmoving piston would tend to force some of the fresh charge out of the cylinder, reducing volumetric efficiency. But completely opposite thing happens at high speed engines. At high speed, what happens is that the inertia of the incoming charge at high speed engine is very high due to high velocity, and as a result the intake can be left open for much more time beyond the BDC, just because the velocity is higher, and as a result the inertia of the incoming charges are higher. So when the piston moves towards the TDC for the compression stroke, the inertia of the incoming charges does not let the fresh charges to get out of the cylinder. Now, for low speed engines, it is seen that the exhaust opens at 25 degree before BDC, but for high speed engines the exhaust is seen to open at 55 degree before BDC. Now, as the exhaust opens before the piston reaches BDC, during the expansion stroke, a part of the work done by the expanding gases reduces. Now, if this exhaust would have opened over here at BDC, then the power stroke would have extended, and as a result we could have got greater work. But if the exhaust is opened at BDC, what happens is that in order to drag the exhaust gases out of the cylinder, an extra amount of work has to be done. Now, this extra amount of work that has to be done can be reduced by opening the exhaust a bit before BDC, and as a result we can say that an overall gain in the output can be achieved. So due to the early opening of the exhaust, we may lose some work from the power stroke, but if it is opened at BDC, extra amount of work has to be done to move the gases or exhaust gases out of the cylinder. Now, this amount of work that has to be done to drag the gases out of the cylinder is much more higher than the loss of work that we lose from the power stroke. So in an overall from the overall view, we can say that if we open the exhaust a bit before BDC, then we are going to have an overall gain in the output. Lastly, it is seen that the exhaust closes at around 20 degree after BDC at high speed engines, and at 5 degree after TDC in low speed engines. Now, during the exhaust stroke, what happens is that the piston forces the burned gases out at high velocity. If closing of the exhaust valve is delayed beyond TDC, if it is delayed beyond TDC, then inertia of the external gases tries to carry out all the gases left in the clearance volume. This results in increase in volumetric efficiency, and as a result the exhaust is left open a bit even after TDC. Now from both the diagrams we can say that from here, first diagram, here the inlet takes place and here the exhaust closes. For the next cycle, definitely the inlet will start from here. So at this region it can be seen that both inlet and exhaust valves are open. So it is observed that both inlet intake and exhaust valves remain open or partially open for a period of time. Now this is termed as the valve overlap. You can see it over here too. Here intake starts and exhaust ends. When the exhaust ends, the intake for the next next cycle starts from here. So you can see that overlapping of those intake and exhaust occurs. This is called valve overlap. Now the valve overlap must not be very high. It must not be excessive enough, because if it is excessive, then we will see that some fresh charges will escape through the exhaust valve and some burned gases will be sucked into the intake manifold, which would decrease the efficiency of the engine. So there are no numerical problems from this chapter. I will be giving you the notes in PDF format after the video is available online, and in the next day I will give you some important questions from this chapter, and day after tomorrow I will be taking a class test on this chapter and the questions will be all MCQ based. Okay, so all of you stay at home and stay safe.